Welcome to Miami. So this is a conference on Hodge theory, birational geometry, and atoms. And so let me let you know, a friend of mine, a collaborator of many years, with scientist and humanitarian Tony Pantev. Tony.
Thank you. So I want to apologize to those of you who have heard me speak about this because I'm going to recycle a lot of the stories that I told before. Hopefully some will be new, but somehow the idea was to set the stage for the interesting stuff that's happening later in the week and recall the framework for this additive invariants or obstructions to rationality that we'll be discussing. So, so I'm giving two talks, and they're based on joint works with Ludmil, Maxim Kontsevich, and Tony Yu, and some of those are in progress. So the plan is first to discuss and hopefully finish this quickly, but probably will take most of the first hour. Some introductory story about what Hodge atoms are, and so I'll start with the standard motivation I always present and discuss the technical tool, which is the notion of F bundles and the composition theorems. I'll introduce Hodge atoms. I'll talk about the way they present obstructions to rationality. Then for the rest of the time, I'll talk about refinements of the notion of an atom, which makes the atoms stronger obstructions. So I'll talk about integral structures on atoms and how one can describe them, compute them, and use them to eventually. I mean, I'm not going to talk about how one uses them to get obstruct rationality, but I mean, I'm not going to do any examples, but the idea will be clear. So yeah, so this requires some serious technicalities. So I'm going to talk about some dual description of Hodge atoms and then explain how one can enhance them with integral structures. Okay, so let me start with this motivation. I don't know how useful it is to people, but to my mind, it's really useful. So it starts with the notion of a non-commutative rational Hodge structure. And that's some essentially linear algebraic data, or slightly deformed linear algebraic data. So it consists of a vector bundle, say algebraic one over the complex line. Then there is some Q structure on that vector bundle, which is specified away from zero. So it's a Q local system, vector spaces, vector subspaces generating the sheaf of homomorphic sections. And then there is a meromorphic connection on H, which has pole at the origin, and the order of the pole is bounded by 2. And the connection, of course, is integrable because we're on a curve, but we require that the rational structure is flat with respect to the connection. There is a really subtle condition which says that the rational structure is the Betti version of connection with the regular singularity. So there is a condition that says that this rational structure is compatible with the Stokes data of the connection. And then there is one other condition which says that if you use the rational structure to define a complex conjugation on to lift the complex conjugation on the base to a complex conjugation on the total space of the bundle, then you can glue H with its complex conjugate where you put the complex conjugate around infinity. And once you glue it, you get a homomorphic vector bundle, and the condition is that that homomorphic vector bundle is stable. So these are this is the package defining pure non-commutative Hodge structure, and it's working.
Tony, could you explain what you mean by this extension H act? And so, how is complex conjugation act?
Right. So H is just a bundle of something.
Yeah.
Right. Once you have a rational structure of it, you have a real structure.
Yeah.
So you have a complex conjugation.
Okay.
So that means that it becomes an equivariant bundle on C with respect to the complex conjugation on the base. And if you conjugate it, it will become a bundle defined near infinity. So the complex conjugation is the one that the real structure of Q1 is the one that conjugates. C goes to -1 over C bar. And you can now glue the two on the unit circle. And when you glue them, you get something formal. So yeah, so unfortunately cannot point.
So, Natalia, maybe you can fix this.
I'll use the mouse if you want.
Oh, maybe the mouse. Thank you. Yeah, so I just want to say what this thing is. It's the analog of a Hodge filtration. And so the condition that the rational structure is flat is the condition that the Hodge filtration and rational structure are compatible. And the ultimate condition is that, so the complex conjugate piece, the chart around infinity is the complex conjugate of the Hodge filtration. And this condition is the analog of the Hodge filtration and the complex conjugate of the Hodge filtration being composed in this non-commutative. And this type of structure is what you expect to see on the cohomology of a smooth and compact non-commutative space, where you think about it as a smooth and compact DG category. They are Z2 graded versions of classical pure Hodge structure. So I didn't say this, but I did say H is Z2 graded. So they're Z2 graded versions of classical pure Hodge structures. And in fact, classical pure Hodge structures are a full subcategory of the category of these guys once you periodize with respect to the action of the data. So you fold the Z grading into a Z2 grade. And now as in usual Hodge theory, families of spaces in usual Hodge theory give you variations of pure Hodge structures. Small proper families of spaces give you variations of Hodge structures. And if you have families of sheaves of smooth compact categories, they give you variations of pure non-commutative Hodge structures. And the way the variation data is encoded is to say that if you have a parameter space, the connection extends into a connection differentiating along the parameter space. And it will still, it is still allowed to have singularity at the parameter space cross zero at the divisor, but the singularity in that parameter space should be regular.
Tony, can I ask again? When we say non-commutative space, you're thinking something like the Drag-Katzarkov sheaves on a right or something behaving in that like
something behaving like that. So it's going to be like a smooth compact category.
Yeah.
But yeah, one example will be
And then the question is, so what is the notion of cohomology that's relevant here?
Oh, it's so the rank cohomology is the periodic cyclic cohomology of the category. The Lubbock cohomology is the Hochschild cohomology of the category. And on these bundles of periodic cyclic cohomologies, you get this notion.
So maybe my question also is, if you have the derived category, you can consider the Hodge there's the difference between sort of the algebraic K theory of the category versus this sort of thing that sees the entire cohomology ring of the variety. This I think it's called topological K theory. So which is one of those relevant?
Right. So the fibers of our bundle will be the periodic cyclic homology in the category.
Yeah.
The rational structure will be given by the image of the topological K theory.
Okay, that's nice. Thanks.
With some twists. So we'll actually come to that in the second part. Okay, but this is somehow the origin of these guys, and this is what we work with in homological mirror symmetry. And one thing that we've learned by doing many analysis, many situations in the homological mirror setting, is that these non-commutative Hodge structures, they capture a lot of the various geometries that appear on the two sides of homological mirror symmetry and linearize those geometries in some sense, the same way usual Hodge structures linearize geometries, but they're very hard to compute and classify. And one, or maybe the biggest obstacle is that I've been talking about algebraic objects here, algebraic vector bundles, connections, homomorphic connections, and things like that. If you want to really define this type of data for a symplectic manifold, so for the Fukaya category of a symplectic manifold, then this algebraicity is unknown. In many cases, it's conjecture, but it requires, even the analyticity is unknown because it requires convergence of the quantum. So you have to struggle with this, but also the structure is very hairy, very complicated. In particular, this compatibility with the Stokes data causes all sorts of difficulties. So you would like to have something simpler, something more computationally viable. And this leads to the notion of an F bundle, which is some kind of a partial projection of the data of a variation of non-commutative Hodge structure, which is more tractable. Okay, and because you have to deal with this convergence and analyticity issues, we'll do it. So we will work with this in the non-Archimedean setting. So I'm going to give the definitions starting with non-Archimedean type of symmetric data. So fixed norm field, in fact, so it's going to be equal characteristic 0. And in fact, for all the considerations that we ever look at in this picture, it will be really the field of Q isosceles in one variable over Q over Q bar. And we'll take D to be the germ 0 of a one-dimensional analytic disk over that field. The variable on that disk I'll call U. Little o will be the close point. And now an F bundle on some space B will be the data. So there will be a substrate of the bundle, which is space B. And then the substrate will be a K analytic supermanifold. Then we'll have a super vector bundle over B cross that disk and a meromorphic analytic connection on that bundle, which has poles at most at U equals 0. It's going to be integrable everywhere. And it will have at most the second order pole when we differentiate in the U direction, and at most the first order pole when we differentiate in any other direction. So this is basically, if you suppress the noise of dealing with non-Archimedean analytic things, it's what we had in the variation of non-commutative Hodge structures, except that I'm ignoring right now the rational structure business and I'm ignoring the positiveness condition. So it's just somehow the family of cohomologies plus the Hodge field. And so it's part of the data that we were considering before, but it's sufficiently good part of the data.
Sorry,
Yes.
I just wanted to ask, so yeah, in this context, the notion of analytic space is the sort of the Kontsevich one?
Yes. I mean, you can do either Berkovich or you could do just rigid analytic geometry with rigid points. The theory is completely equivalent, and for certain considerations, actually we restrict to just looking. I mean, we always work with the virtual Berkovich spectrum, but we sometimes just look at neighborhoods of rigid points. But there is no penalty in the whole theory if you just work with rigid analytic spaces.
And just to be clear as well about the supermanifold, supervector bundle, that's just this sort of even on.
Yeah, even on.
Yeah,
So the odd part doesn't. The odd part is purely polynomial, right? Because these are finite dimensional guys.
Yeah.
So.
Well, play this for a roll.
So they. I mean, they're there. You need them, but they're not affected. The analyticity is not affected, right? Analyticity is a statement about the even part. Okay. So once you get one of these guys, bundles, you get a lot of pieces of it that you can play with it. So a lot of residual structures. So one thing you get is just a bundle on B, because you have a close point on the disk and you can restrict to the parameter space close to close point. So you have a super manifold and a super vector bundle on that super manifold. What you get also is if you take the connection nabla, you can take U times nabla. Now it just becomes a differential operator with a symbol that's the identity multiplied by U, and you can restrict it to the vertical direction for the projection map from B cross D to D. So now you get a family of connections. So if you view this as a family of spaces over D, fiber B, parameterized by D with fiber B, you get a family of vertical connections, but not quite connections, they're U connections by restricting to the nabla to the differentiation in the vertical direction. So this is some kind of a twistor object that we commonly study in non-abelian Hodge theory, is U connections. And it's a useful object to keep in mind. It's simpler than the general connection that differentiated that. Now, if you have a U connection, you can specialize it to U equals 0, and we get a Higgs field. So we get a map from that bundle H0 to H0 tensor with omega 1, which is integrable. So it's all linear map and it squares to 0. And we also get some extra information piece, which is coming from the second order pole in the U direction of our connection. Is the coefficient in front of the second order pole, which we call kappa, and this is just an endomorphism of the bundle. And it commutes with theta. This just follows from the integrability now. So the F bundle H nabla B gives you all of these objects, so theta, so H0, theta, and kappa are the important ones to remember, because we'll be using them over and over. Now, why is theta important? Because it gives you an algebra structure. So this contraction with theta gives you a map from the tangent bundle of B to the endomorphisms of H0. So you get a way to view vector fields on B as endomorphisms of the bundle H0. And again, the integrability tells you that the collection of endomorphisms that you get by mapping vector fields commutes. So the image of the tangent bundle in the endomorphism algebra of the bundle H0 is a commutative set, sheaf of commutative subalgebras. And that bundle is called maximal at the point if this sheaf of commutative algebras has a cyclic vector, so that the induced map from the tangent bundle to the bundle H0 is an isomorphism. And maximal at every point. It's maximal if it's maximal at every point. And it's just a technical thing, but what it really says is it says that once you have a maximal at bundle, then the tangent bundle, first of all, the bundle H0 is isomorphic to the tangent bundle, and the tangent bundle inherits an algebra, a structure of a unit though commutative algebra. And if you have a maximal bundle, so you get this unit of commutative associative subalgebra, the endomorphism bundle of H0, which is actually isomorphic as a bundle to H0. And this is what Kaplan and Manning call an F-manifold. The difference is that they work with complex analytic F-manifolds. This is just a rigid manifold. This guy is also equipped with a particular marked vector field called an Euler vector field. It's a section of the tangent bundle. It's the one that corresponds to kappa. Kappa is a particular endomorphism of H0, and it happens to be in the image of that algebra. So it commutes with everything, and that's the Euler vector field. And the powers of that guy generate the algebra vector, polynomial vector fields on the circle. So there's this humongous infinite dimensional algebra that analytically acts infinitesimally on our manifold field. Now, if you have a rigid point, then so the utility of these F bundles is that they have very restrictive structure. They satisfy decomposition properties. The first one is the decomposition theorem, the spectral decomposition theorem, which says that if you break the fiber of the bundle H into generalized eigenspaces for the operator kappa, then the whole geometric object, D, H, and nabla, decomposes into pieces which are which correspond to these pieces in the fiber. So the manifold decomposes locally into a product of manifolds. The F bundle decomposes into a direct sum of F bundles, and each of the F bundles is a pullback from the corresponding part. So formally, this is not a very mysterious statement, but it requires some work to actually prove it analytically, and that was done by reaction.
So this decomposition is local on the.
It's local at point. Yeah, local near each point. Okay. So there is another decomposition theorem which doesn't work for arbitrary F bundles, but works for the F bundles that we really care about, which are these A-model F bundles. So those are the ones that are associated with the smooth projective variety, in fact, with the universal family of Fukaya categories of a compact symplectic manifold or a smooth projective variety. So let me just recall what these guys are. This doesn't work. Okay. do this. Sorry, I'll have to scroll to the very back. Ah. So if you have a compact symplectic manifold, and just for simplicity, let's assume that the symplectic form I'm taking, I mean, this is not really needed. It's with integral periods. Then for every homology class, we get genus 0 Gromov-Witten invariants in that class. So the images of the virtual fundamental classes of the modular space of stable maps by the evaluation map into the product of n copies of X give you algebraic cycles. And you can package those into generating series, which is the genus 0 partition function for the corresponding two-dimensional QFT. And so it's given by coefficients which are integrals of basic classes in the cohomology on these cycles, and that they're variables which are duals to the basic classes, which just keep track of where the coefficient sits. And then there are also bookkeeping variables that keep track of the symplectic area of class A. And so this this function is a formal Laurent series with coefficients in Q and formal Taylor series with coefficients in the variables on the cohomology, linear variables. If you take the field to be the Puiseux series, in fact, you can put coefficients in Q bar, then F0 gives you an analytic function on a particular open set in the space, the rigid analytic space corresponding to the cohomology tensor with K. It says ball there. It's not quite a ball. It's a product of tori, polydisks, and vector spaces. F0 is a convergent analytic function of the open guy. Using the Poincaré pairing as usual, we can take the derivatives of that function and define a quantum product on the bundle with fiber to cohomology. You take the trivial bundle with fiber to cohomology and you equip it with a quantum product by this formula. And then the A model bundle or quantum D module is the bundle for which we take this HX guy with fiber to cohomology. The connection is given by these formulas in the direction of the cohomology. It differentiates with the first order pole, where the coefficient in front of the first order pole is just the quantum multiplication with the basic class delta. And in the direction of U, so the non-commutative Hodge filtration, it has a Laurent tail of length 2. So the coefficient of in front of 1 over U is the grading operator of the cohomology, which multiplies the degree I cohomology by I minus the dimension of 2. And the coefficient in front of the second order pole is this is this Euler vector field. So it's quantum multiplication with the cohomology class, which in degree 2 is just the canonical class. And in higher degrees is just the universal class corresponding to the point cohomology where you're sitting, up to a rational factor, half integer factor. can I go back? Yeah.
Yeah, we use the maximum construction, the torus of degree 2 is has lower dimension than the classical. So it's not over maximum, but maximum construction.
This is well, yeah, this is the maximum. Yeah.
Can you explain the origin of the parameter U with the table?
Why do you need U?
Well, I mean, so in your previous slide, you had the definition of the big quantum product, and then on this slide, you've introduced this variable U that's going to play a big role. I've never quite understood. I mean, I understand it's something like rotating the loop in the Hamiltonian work homology, but maybe you could add some. I don't know, maybe, or we could get it.
Yeah, I mean, I don't have a clue. I mean, yeah, this is
okay
for
let it go.
Mary Duncan. Yeah, I don't have the from the point of view of an F manifold, you can always introduce the parameter U to capture the data of the second order pole. I mean, the F manifold datum, it's not just an irregular connection. It it has this Euler vector field, right? And that Euler vector field commutes somehow with the data of the regular connection. And so you can look at this kind of a twist of deformation of that manifold datum. And you need to introduce it at the second order in order to have something flat. And so it's very natural from that point of view, but it's again ad hoc. I don't see any conceptual. I mean, I'm sure there is one. So let me. Why am I? Here, right? So if you have the same model of maximum A model F bundle, there is a remarkable blow-up theorem due to Iritani, which says that if X is a smooth projective variety, and you blow up something smooth, then you can find some special points in the opens that we have in this B for X hat and B for X and B for the center of the block, so that when you identify the homologies by the usual block decomposition, the neighborhoods of those points get identified, and you get them in the decomposition of the F bundle. So the F bundle for the block decomposes into a product of F bundles for pieces, one for the thing that you're blowing up and co-dimension -1 pieces for the center. And one can check that this works rigid analytically as well. And so this is the second decomposition property of F bundles, but it's really for the same order F bundles. It's straightforward to check that the block formula is compatible with spectral decompositions on both sides. And so the pieces in the spectral decomposition of the model F bundle you can try to use them as abstractions to or the detection method for block relations. And to formalize it, you can't just keep track of the pieces, but you also need to look at their natural symmetries.
Tony, I think you forgot to mention that you're going to restrict your insertions to algebraic classes.
Yeah, so let me just say so far this was true for the F bundle that corresponds to any two-part symplectic manifold, and the previous decomposition theorem, the spectral decomposition theorem, worked for any F bundle, no methodology. But the information that you get from the residual structures given to that bundle of any modular bundle of symplectic manifold doesn't know anything about the any other structure. So your symplectic manifold is scalar or projective. This F bundle datum and the decomposition, they don't know anything. So if you want to really get the block invariant, you need to put that extra geometric information into the mix. And this is where this natural symmetry comes in. You put in that extra information as particular symmetries of these pieces that and the symmetries, these are motivic symmetries, they come from a Manford-Tate group or a Hodge group. So here is what we're going to do. We are going to take the universal Manford-Tate group, which is the Galois group of the Tanakian category of polarizable pure Hodge structures. This is a graded semi-simple category, but our objects were Z2 graded, so you need to get rid of you need to fold the Z grading into a Z2 grading, and the way to do this algebraic in group language is to say that a Manford-Tate group has a character, which is given by the action of the Hodge structures, the action of the Manford-Tate group on the Lefschetz motif on the second homology P1. So you take the kernel of that map. So the representations of that kernel are the Z2 graded Hodge structures, and the Z2 grading is detected by the image of -1 under the standard cocharacter of the Manford-Tate group, which corresponds to the Hodge grading. So the image of -1 exactly gives you the Hodge. It happens to be in the kernel and gives you the Hodge grading. Maybe because this will come up and apparently it is confusing. There is another character for the Manford-Tate group, which is not corresponding to the Hodge grading, but the one corresponding to the offshore grading. So this guy corresponds to P plus Q, the homological grading, but there is another one which corresponds to T minus. That one actually survives. It's in the kernel of pi, and -1 is also in that too. So I could have taken that character, and that one will be using as an invariant anyway. Anyway, so I'm going to call Hodge the kernel of pi, and there is this marked central element of order 2, which is the image of -1. Just giving you the parity of homology grading, or the parity of the Hodge grading. And this is a pro-reductive algebraic group. its representations are the pure polarizable Z2 graded Q4 structures. And the central element just gives you the homology degree, the parity. Now take our favorite non-Archimedean field, take the K-analytic maximal F bundle, and look at the Q-bar points of the Hodge group. It acts by analytic automorphisms. The bundle is equivariant. So now you can pass through the fixed points of that action. So these are just the Hodge classes, the intersection of the Hodge classes with our open in the base. It's a purely even K-analytic submanifold. And it's open in the Hodge classes. And so we're going to restrict the F bundle to that guy. And we'll look at the Euler vector field multiplication on that restricted bundle. And look at the cover of eigenvalues for that operand. So the analytic subvariety is locus of Hodge classes times the analytic affine line, parameterizing the eigenvalues of that kappa. It's a cover. You can reduce it to look at the reduced analytic space and throw away the branch divisor and look at the cover restricted to the complement of the branch divisor. Now you have an unramified reduced cover. And you can look at the decomposition at a given point, and now it's labeled by connected components that cover. And it's well-defined modular analytic continuation. So the connected components of that cover give you these F bundle pieces, which you can think of as invariants. So these guys is what we call atomic F bundles. So the operator kappa has a single eigenvalue on each of them, and the Q-bar points of the Manford-Tate group act on each of these pieces. So they are variations of Z2 graded ordinary constructions. And so if you take the fiber, which is just some Hodge structure of isomorphism, that Hodge structure is well-defined isomorphism regardless of which connected point you're sitting on, because the continuation preserves that representation. And it's a pro-reductive group, so no modular representations. So the blow-up theorem and there is an analog of the Reh-Hirsch theorem, the projective bundle decomposition theorem, says that the decomposition of this F bundle into atomic pieces is compatible with these decompositions. So this leads to this definition of atoms. So the Hodge atoms for a variety are just the connected components of that unramified piece of the spectral cover. And the set of Hodge atoms for all possible varieties are the Hodge atoms for any variety modulo automorphisms, and then disjoint union over all isomorphism class of varieties. And then there is an equivalence relation, which is generated by disjoint unions, blobs with smooth centers, and projective bundles. And now for any atom, you can associate this finite dimensional linear representation of the Hodge group, so of the Z2 graded Hodge structure. And you can look at invariants of that structure. So you can look at the number of the dimension of Hodge classes, the space of Hodge classes in that Hodge structure.
So and the invariants of the Hodge,
Say it again.
I think there's a typo in the definition of row alpha. I just can't quite pass it. The
The superscript should be Hodge, yeah. Just fixed points on the Hodge. And then there is a Hodge polynomial that corresponds to the Hodge thing, which is the one that's above from the biped. And because there is no positiveness in this picture, so there is a positiveness on the sum of these guys. So the sum of those Z2 graded Hodge structures, it's gonna be a Z2 graded Hodge structure for which this Hodge polynomial, the Hodge graded Hodge polynomial will be symmetric with respect to T goes to T inverse. But for the pieces, this is not true. So the pieces are whatever they are. So for every atom, you get such a polynomial. And yeah, the coefficient into the T to the K corresponds to the K graded Hodge. And if you have a smooth projective variety with an F canonical class, the local atoms for that variety is a singleton. There is only one atom. For every Hodge atom, the number of Hodge classes is at least one. And so you get the obstruction to rationality, which says that if you have one atom in the atomic decompositions of the homology of X, which does not appear in the atomic content of a variety of dimension n-2, then X cannot be rational. Okay, so we get this non-rationality of the generic cubic, generic cubic fourfold, because you can compute the dimensions of the with the invariants of these Hodge atoms at a particular point, and they're already restrictive enough. So if you have the information that we use to rule out rationality is to say that if you have an atom or a fourfold that comes from points or curves, or any atom that comes from points or curves, then in its Hodge graded Hodge polynomial, the degree 2 coefficient has to be 0. Just for homological reasons. If you are dealing with an atom of a surface, you can look at minimum models of surfaces and look at one representative of the birational class. If you have a surface which is general type, not general type, or K3, or abelian, or relatively minimal elliptic, then the coefficient T square will be 0. If you have a K3 general type or relatively minimal elliptic, then the canonical class is F, and then you get only one atom, which means that the number of Hodge classes for that atom will be the number of Hodge classes for the surface, and that will be at least 3. So this is what you know about atoms of lower dimensional varieties. And then if you look at generic cubic, very general cubic fourfold, where the algebraic homology is just the powers of the hyperplane, then right, so you get this decomposition into the powers of the hyperplane as the algebraic classes, and everything else is transcendental. And then you can use Giventhal's calculation on P5 of hypersurfaces of P5 at the point which corresponds to the hyperplane in the base, and compute the action of the Euler vector field, the operator kappa, on the powers of the hyperplane. This is what Giventhal gives us. It gives us what the action is always on this ambient cohomology, which is spanned by the powers of the hyperplane, and you write down the matrix and you get 4 eigenvalues. You get 0 and the 3/3 units of unity up to a scale. On the algebraic classes, the 3rd roots of unity have as eigenvalues have multiplicity 1, so you have a single eigenvector, and you get in the 5-dimensional space you get 2 more eigenvectors of eigenvalue 0. So there, in the algebraic classes, there are 2 eigenvectors of eigenvalue 0 and 3 eigenvectors of eigenvalues 3rd roots of unity. And in fact, one can check that the transcendental part also is in the eigenvalue 0 space, but that's not really needed for that. Okay, then what you can do is you can look at the Hodge atoms for our cubic. So the eigenspaces can, so if we move from the special point where we did the calculation to the general point in that open set in the base, the eigenspaces can only split. So you get 4 atoms, and these atoms can have a number of algebraic classes in them, at most 2, because the 1-dimensional atoms have 1 algebraic class, and the other guy has at most 2 algebraic classes. And there is at least 1 atom with coefficient in front of t square not 0, because there is this 1 here. So for that atom, we can have at most 2 algebraic classes, and so that cannot be an atom of the point curve for the surface. So that's the obstruction.
Just a priori, it could be the 24-dimensional thing splits.
It could,
but that's.
but it doesn't affect that obstruction. Yeah. So it's a very soft obstruction. Okay. So it's a very soft obstruction, and one consequence of it is that there are very few examples where it can actually give you information. So for the cubic, it gives you some insight, but if you try to find other examples, it's difficult. So one way to remedy this is to refine the notion of a Hodge atom and add back the structures that we ignore. So we can add some type of Euler and ortho-chi pairing on the cohomology and check that atoms inherit the atomic decomposition is orthogonal with respect to that pairing. And we can put rational or integral structures. And those have to be the rational or integral structures that you see in symplectic geometry. And check then that the pairing and integral refinements are compatible with the decomposition theorems. And then you'll get these refined atoms, which have pairings and integral structures. And those will be much more sensitive than the atoms themselves. So you can get examples that you cannot detect by just looking at atoms. Okay, and yeah, so they obstruct rationality, so you can build some examples for quadric surface vibrations, and presumably more examples. But you need to really work on these refinements. So this is what I'll try to explain next. Please. 5 minutes. Okay, I'll start and we'll continue after the break. So now what I'm going to try and explain is what are these integral structures on A-model and bundles. How can you make them work, and how can you see that they retain the atomic position? So there will be a lot of technology, and I'm trying to present it in some kind of a historical way. So these integral structures for A-model bundles, they exist conjecturally, but historically, when we started looking for them and introduced them for the non-commutative Hodge structures, we were always assuming that the quantum product is complex analytically convergent. So and there, you know, the structures make sense, and you can kind of pin them down by computing some geometric examples and using normalization. So I'm going to try to explain that a little bit, and then we'll switch to the non-Archimedean setting and see how these structures can appear there. So suppose that we have a complex analytic area. Now I can define what the Z structure is, or Q structure is, or complex analytic area bundle. So complex analytic area bundle is again what we had before. It's a super vector bundle or super manifold cross a germ of a complex analytic disk. It has a Z structure, a Z local system, which is flat with respect to the connection. The connection, so the end bundle data is again a connection with also second order pole in the U direction and first order pole in the V direction. The Z structure has to be flat with respect to that connection and should be compatible with the Stokes structure. And I'm not going to talk about what compatibility with the Stokes data means, but I'll tell you exactly what it means in some equivalent language, which actually will make sense in the rigid analytic set. But this is one of the things you have to deal with. You need to say what compatibility of Betty data is with Stokes data. So in the complex analytic setting, we have the irregular Riemann-Hilbert correspondence. So we know what that means. But in the rigid analytic setting, we do not have. So we need to do something.
Tony, I remember in your paper you mentioned that because you're working rigid analytically, you don't need to worry about Stokes phenomena.
That's what we are doing with the Hodge atoms.
Yeah.
Once you start putting structures, integral structures, or Q structures, you need to worry that you are not putting integral structures or Q structures that are too flat. So some remnant of compatibility with Stokes data should be there. And I mean, you know, of course, the Q structure that we care about is a particular one, but it's a good idea to check that this robustness is really there. And in fact, if you want to construct it, this compatibility with quote unquote Stokes data in the rigid analytic setting is something that pins it down. So you can really work with it.
So Tony, but does it mean that in the end you have to stick with this convergence plus the bridge of convergence hypothesis to the models?
Say again?
So it means that in the end you're going to like have to somehow assume positive radius convergence for a model to do this sort of
For the analytic one?
Yeah.
Well, here to do the definition, I will. But then I'll rephrase it in some different way. And that different way will make sense in the rigid analytic setting.
So yeah,
And we'll... Okay. So this triple extends to the whole complex line from the disk, and the extension is algebraic in the U direction just by the Delian extension. The local system extent support potato. You know, I mean, we are taking it to be a local system of a free finite generate abelian groups, but you can refine it to arbitrary finite generate abelian groups with some condition on the torsion. And I'll mention something about this later. What you really want to do is you want to say what all of these conditions mean in the non-Archimedean setting. And as I said, we don't have the Riemann-Hilbert correspondence, so we cannot do it this way. We need to do something different. The different thing we're going to do is we're going to do a Fourier transform. And I'm actually out of time, so maybe let's take a break and we'll